All right, so before we dive a little deeper into series, I want to just sort of summarize the results that we've seen, or at least some of the results that we've seen leading into this discussion. So remember, we can discuss sequences, we can discuss series. There's a difference between the two. Whereas a sequence is just an ordered collection of numbers, the series is a sum of the ordered collection of numbers. So as I'm noticing here, we've got to put plus signs between all of our objects. So essentially just take the terms of a sequence and add them all up. Now, if you have a finite number of numbers in your sequence or series, we refer to those sequences and series as finite sequences and series. And the sequence or series is infinite, should there be an infinite number of numbers associated. Now, since series are so frequently worked with here in this part of the course, a way to concisely articulate them is to use sigma notation. So when you look at sigma notation, remember that the number down below instructs where to start, the number up above instructs where to stop, and then the AI is just referring to the individual terms of the series. So this series will stop when you get to the nth term, whereas this series with infinity on top will actually never stop. Now, one of the major goals of this section of the course is to get a familiarity and to get a grip, really, of how to add up an infinite series, how to add up an infinite collection of numbers. And well, the way that we do this is we essentially do it with limits. Instead of looking at the sum of the first 10 numbers or 100 numbers, we look at the sum of the first n numbers as n goes to infinity. We use limits in order to accomplish this. Now we know anytime we evaluate limits, we could refer to the limits as divergent or convergent, depending upon if the limit doesn't exist or if the limit is plus or minus infinity, or if the limit evaluates to a real number. Now, the primary tool that we have so far in terms of determining if an infinite series is divergent or convergent is the divergence test. And this essentially says that if you look at a series whose terms limit to a non-zero value, here is an example. Note these terms are limiting to 1. Well, that means this sum is effectively, eventually, a sum 1 plus 1 plus 1 plus 1 perpetually. Now, it doesn't matter how many times you add 1 to itself, if you add 1 to itself an infinite number of times, you will definitely get infinity. It doesn't matter what non-zero number you add to itself an infinite number of times, you will end up with an infinite value as a result. So should the terms of your series not go to 0, you can be certain that those series land among the divergent series. This is why we call this test the divergence test. Now, the divergence test only tells us something about series whose terms do not go to 0. Should your terms go to 0, well, it's actually possible for the series to diverge or converge depending upon the nature of the series. So that's going to be essentially where we focus our attention here moving forward. And what I'd like to do today is to discuss a particular collection of series that sort of could fall under this heading of the series whose terms go to 0. And so let's take a look at these series today. And in fact, so now here we'll have, when we discuss these series, we'll actually have a nice robust collection of series to discuss. And these series are referred to as geometric series. Why they're called geometric series, essentially you can draw geometric pictures associated with these. But that's not all that important, I suppose, but the name is what it is. So what are the geometric series? So the geometric series are sums that are essentially like an exponential function. You've got some base down here, we're going to call it r, and that base is going to be raised to higher and higher powers with each successive term of your sum. So r is just some number off the number line, and then the n starts at 0 and goes to infinity. So if you want to look at what a partial sum would look like, remember a partial sum is just the sum of the first however many numbers. Well, the first number in our sum is r to the 0, because our sum starts at n equals 0. The next term r to the 1, r squared, and so on. So if you want to add up the first capital N numbers, get the nth partial sum, well then you would just get r to the 0 plus r to the 1 out to r to the n. Now, it would be wonderful if we could get the value of this partial sum like known to where we could compute the limit as n goes to infinity. Because if instead of adding up the first 100 numbers or 1,000 numbers, we look at the expression for the nth partial sum as n goes to infinity, that would give us the sum of all infinitely many numbers of our series. That would give us the value of our series. That'd be great information to have. So in order to get to that point, what we're going to do is do a little bit of algebraic manipulation. So note, this equation has two equal things. It has the nth partial sum, which by definition is the sum of the first n terms in the sequence, or the sum of the terms up to capital N, and that's exactly what we've got here. Well, since we've got equal things, we could do the same thing to both sides, and we'd still get equal things back in return. So what we're going to do is multiply the left-hand side and the right-hand side by negative r. So just so we're clear and we're on the same page, what we've done here is we've multiplied by negative r. Now, on the left-hand side, you just get negative r times the nth partial sum. And on the right-hand side, what you can notice is, if you take negative r times r to the 0, you'll get negative r to the 1. And r to the 1 times negative r is negative r to the 2. Eventually, you'll get up to like r to the n minus 1. Multiply that by minus r, you'll get r to the n. And then r to the n multiplied by negative r would be negative r to the n plus 1. Now, what's interesting about this and why this multiplication by minus r was convenient for us is we can now add up left-hand sides and right-hand sides, because we have equal things on line 1 and equal things on line 2. And if you add equal things to equal things, well, you'll get equal things back in return. So on the left-hand side, we'll get Sn minus Rsn. And on the right-hand side, note, there is a lot of cancellation. Because when you add up what's in the first line and the second line, the R1s ultimately cancel, because above R to the first is being added and below R to the first is being subtracted. Similarly, R2 is being added and subtracted, Rn is being added and subtracted. And in fact, everything between R2 and Rn, same story. So the only terms that result on the right-hand side are actually R to the 0 minus R to the n plus 1. Okay, a little bit more manipulation. Note, both of these terms have an Sn as a factor. You could factor that out. You'd get 1 minus r. That's perfectly well and good. And this is actually really well and good because we're trying to get a formula for Sn in order that we take the limit as n goes to infinity. We want to get a grip on what this series' value is. So we got to get a grip on what the limit of its partial sums are, which means we want to know what Sn is. But check it out. If we just divide by 1 over r to both sides, well, we would end up with Sn equals 1 minus r to the n plus 1 over 1 minus r. And this is now a beautiful formula for S sub n. And what's interesting about this is we actually know precisely when this limit converges. Because note, the only thing that depends on n is this r to the n plus 1 term that's upstairs. And that r to the n plus 1 term upstairs is going to converge as a limit precisely when the value of r is small. Well, smaller than 1 in absolute value. This is a fact that we saw from the previous section when we were looking at sequences. If you have a multiplier which is relatively small, less than 1 in absolute value, well then when you continually multiply by that multiplier, you'll get something that recedes to 0 in value. So, should your r be less than 1 in absolute value, which is what we have, we actually know exactly what the limit is. The limit of that r to the n minus 1 term is going to be 0, which means that when you look at this fraction as a whole, the limit as n goes to infinity of this whole fraction is going to be 1 minus 0 over 1 minus r, which is just 1 over 1 minus r. But now let's remind ourselves of what this limit is. This is the limit of this ratio, but that ratio is the value of the nth partial sum. So this limit is the limit of the nth partial sum. So this is not, this limit is not the sum of the first 1,000 terms or million terms. This is the limit of the sum of all the terms as n goes to infinity, which is effectively the sum of our original series. It's effectively r to the 0 plus r to the 1 plus r squared plus dot 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 forever. Precisely the sum from n equals 0 to infinity of r to the n. So what do we see? Well, what we see is we have a formula to describe what the sum of our geometric series is. And in fact, we could take this formula and generalize it slightly, if I may, to put this all together here. More generally, if we take this sum and we multiply it by c. So this is just distributing in a constant throughout. That would be totally well and good. Well, then you would just get a constant times 1 over 1 minus r, which is precisely c over 1 over 1 minus r. And this would hold true when absolute value of r is less than 1. When absolute value of r is not less than 1, we're in the situation where this limit diverges, and well, hence, we're in the case then where the limit of the partial sums diverge. We're in the case where the series diverges. So this series, which we're going to call a geometric series, is divergent precisely when the absolute value of r is greater than or equal to 1, and this series is convergent precisely when the absolute value of r is less than 1. So not only, though, do we know that the series converges, note we have the actual value that this series converges to. It doesn't just converge to some number on the number line. The value it converges to is c over 1 minus r. And this can be, no pun intended, fairly valuable to us in the sense that it allows us to determine what the value of a sum of this form is equal to. So take a look at this sum here, 8 over 3 minus 16 over 9 plus 32 over 27 minus 64 over 81. I claim this is a geometric sum. Now, to be a geometric sum, we would have to be able to factor out a constant, and I claim we can factor out a constant from all of these terms. Moreover, we would have to have our first term correspond to r to the 0. Note, by the way, the first term here would have to be r to the 0, and we can play that out, right? Because if you think of each of the terms as 8/3 being factored out, you could do that, right? Because note, you could factor out 8/3 from the first term, and if you did, the first term would correspond to r to the 0, or 1. So this would correspond to r to the n, where n equals 0. Now, I claim that this expression holds all the way through for each of the terms. Check it out. What about when n equals 1? You would get 8/3 times, well, oh, I guess we have to figure out what r is now that I'm looking at this. What is r? What's going to be the ratio that's going to get us from one term to the next? So 8/3 is the common factor that we can factor out. Now the question is, what is the r? Because we know in the first case we get the r to the 0 case. We have 8/3 times 1. So now the question is, what is the r that we're going to be raising to the nth power? And well, that can be determined by looking at what we would need to multiply by to get from one term to the next. Note, upstairs we multiply by 2, downstairs we multiply by 3, but actually that doesn't fully account for the values of the terms here. We also have a minus sign coming in. So let's say we multiply by -2 upstairs. That would do it, wouldn't it? Because that would give us a -16 over 9. That would work. And check it out. When you get from one term to the next, multiply by 3, multiply by -2. Same story, -16 times -2 plus 32. Everything's working out great. So the r here is going to be -2 over 3. And so to write that out, we'd have -2 over 3 to the n. So put it all together. Note, the -2/3 is less than 1 in absolute value. So that means we fall under the initial heading here, which means that our sum is simply c over 1 minus r. C is our constant, 8/3. 1 minus r is 1 minus -2/3. So that's 1 plus 2/3. Put that all together. Downstairs we'll get 5/3. Upstairs we've got 8/3. That's going to be 8/5. And if you really think about this, this is almost an amazing result, because what we have done here in this sequence of steps, dating back to whenever we first discussed how to get this formula, is we now have just added up infinitely many numbers, and we have determined exactly what the sum of those numbers is, 8/5, which is pretty damn cool when you think about it. Now, what about this guy below? This sum is, well, I claim also a geometric sum. And that may not be immediately apparent, but we can make this so. Now, note, we've got to get the terms in the form n equals 0 to n equals infinity. So this sum we're going to have to re-index in order to make work. Now, note, the first term had 5 to the 4th downstairs and 7 to the 6th upstairs. So if we're looking at the terms of this series, 7 to the 6th, 5 to the 4th was the first term. Now, in order for our re-indexing to add the exact same terms together, we still need, corresponding to n equals 0, 7 to the 6th upstairs. Well, that's going to be 7 to the n plus 6, because, well, 0 plus 6 would give us the 6 that we're after. And downstairs we need 5 to the 4th, but 5 to the 4th should be yielded for n equals 0. So that's going to be 5 to the n plus 4. Okay, sweet. So we've got our sum re-indexed in the proper form with n equals 0. Now, what do we need to do? We've got to factor out a constant so that our first term is just r to the 0. So think about what our first term is here. Our first term is 7 to the 6th plus 5 to the 4th. Well, that means that that is our constant that we're going to factor out from all of our terms, because the first term needs to be a constant times 1, in effect, a constant times r to the 0. So we factor out that constant, and what do we get? We get 7 to the 6th over 5 to the 4th times 7 to the n over 5 to the n. And check this out, 7 to the n over 5 to the n, if you wanted to, you could rewrite that simply as 7/5 to the nth power. And if you did, you would have something exactly in our geometric series form. So our constant multiplier that's been distributed through is 7/6 over 5 to the 4th, and our r is 7/5. Now note, 7/5 in absolute value is greater than 1. Well, in particular, it's greater than or equal to 1. And what does that mean? Well, if our multiplier is greater than or equal to 1 in absolute value within our geometric series, that means that our geometric series diverges. So this series is going to diverge, and we now know as well, related to this series, that when you add up these infinitely many numbers, 7 to the 6th over 5 to the 4th plus whatever the next number is in the series plus the next number in the series perpetually, you're going to get something that either is not well defined or is plus or minus infinity.